Okay, so welcome to the 2022 P4 workshop. It's a real pleasure today to have Raghava Sivaramu. He's a fellow at Pensando Systems, and he's the lead developer of an SDN solution for cloud providers. Before Pensando, he held engineering positions at Cisco in CME, Procket Networks, and HP. And he's a prolific inventor with more than 20 patents and patent applications. And he's also interfaced with the internet community, authoring RFCs and internet drafts. So today he's going to tell us about some of Pensando's solutions for using P4 at the host NIC interface. So pleasure to have you. Take it away.
Yeah, thanks for the introduction, Nick. So the topic of today's presentation is leveraging P4 at the interface between the NIC and the host. So the P4 PNA work group has been looking into coming up with an architecture specification for the NIC interface or the NIC architecture. So here we want to talk about the Pensando experience on how we have addressed or solved the P4 interface functionality, some of the use cases at the P4, the host interface. We'll start with talking about what are some of the host interface functions or the use cases that are interesting to us and what we have actually looked into addressing in our product. And then we'll talk about some of the case for programmability at the host interface. Why do we need programmability, and also how you go about implementing a programmable solution. So some of the fundamental design considerations that we have taken into account to come up with an architecture to solve it specifically on the host messaging interface. And then we'll also talk about some of the language and compiler extensions that we had to do to address these needs in our implementation. And we'll in the end we'll close out with an example host IO call flow, taking a use case of an NVMe over Fabric TCP IO sequence. So what are the typical host interface functions that we need to solve at a smart NIC interface? So there are typical use cases in networking, storage, compute, security, in all these areas, where the smart NIC is expected to offer a specific PCI or enumerate a specific like a set of PCIe devices with various capabilities. So the Ethernet IO being one of them, where you need to do handle like standard Ethernet traffic from the host to and from the host over, where you expose either a set of physical or virtual functions to handle the Ethernet data, working in conjunction with like an Ethernet driver, and offer the typical or the classic offloads that are traditionally done in a classic NIC, like the TSO or the VLAN offloads or the checksum offloads and the sort. So in addition, a smart NIC can also offer like a storage kind of a device enumeration, where you can like expose NVMe volumes to the host and in the backend do a virtualization of NVMe over fabrics. So to the host, these NVMe devices would look like local drives, local volumes. But in the backend, the smart NIC could do a block storage virtualization solution of taking the traffic over the network over the fabrics. With various transports like TCP or RDMA. And there is RDMA use case where you want to implement like remote DMA services for various compute or storage applications without incurring the overheads of the host CPU usage. And also there are the crypto or look-aside offload kind of capabilities using like crypto dev, like a use case with DPDK applications, for example, where you do like a request response kind of a model to do cryptographic services or encryption services to the host data. Another aspect of where the host interface functions come into the picture is applying smart services or extending the smart services to host applications, where typically the functions that are done on network devices, the switches or routers, or like specialized appliances, like these could be the L2, L3 services, IPsec encryption, or so layer 4 to layer 7 services. You bring them closer to the applications by doing it in the smart NIC, and you apply these services for the host traffic as against just doing it on packets or in the network layers. So some of these considerations actually make a case for programmability. That there is an option that some of the traditional smart NICs have approached on how to solve these by using a combination of a fixed function logic and a set of general purpose CPUs. But there are kind of downsides with using either the fixed function logic or the CPUs, where the fixed function logic lacks flexibility. And with changing requirements, there are with various Ethernet I/O services, for example, there are different descriptor formats for the VertIO, VDPA. There are some standard-based, some proprietary use cases to be able to handle different types of descriptors or message formats from the host. The VM XNet UPT is the VMware specific use case, virtual NIC use cases where with universal pass-through, where the VMs can bypass the hypervisor and be able to communicate to the NIC device directly. So the handling of all these types of messages from the drivers or the descriptor formats are lead to the scenario where you want to have the flexibility of programming or handling or interpret the messages differently. So in addition, doing these advanced services like the NVMe over fabrics, for example, where the NVMe over fabric standard itself is evolving, and you have different ways of handling them and translating them into different transport technologies and stuff. In addition, doing the encryption and compression at various layers of data, whether it's the overlay or the underlay kind of scenarios where the requirements are kind of dynamic to be able to apply on different layers of data. So that kind of says that the fixed function logics based solutions are not conducive to be able to handle dynamically. So the CPU kind of based model where you just run all these applications using open source code and port them into ARM or the MIPS kind of cores has the implication of performance, specifically where there's a need for high rates of packets per second or connections per second handling, where you want to do stateful processing of keeping state and updating state on a per packet basis. And in addition, it's basically a challenge of maintaining performance at scale, where the more the databases grow and the more instructions you have to process or the more amount of memory you need to access, the performance varies and you're not able to keep up the high rates of the throughput that you need with general purpose CPU-based processing. So this leads to a conclusion that you do need domain-specific specialized instruction set processors to be able to handle these in like a pipelined architecture. And that's what we talk about next on how do you go about bringing in the programmability at this layer. So, the approach we have taken is you leverage the typical switch or packet-based P4 programmable architecture that's there with a standard switch P4 interface, where you do get multiple match action units that you can leverage to process multiple packets at a time and stuff, and you extend that execution model to go beyond packet processing. So, I mean, the key need here for a host P4 interface is to be able to handle packets in and out of memory, and be able to handle the work as in terms of message processing. So we will go a bit into how a host P4 interface architecture is defined, or what extensions we had to do to enable a host P4 interface. So one of the if you contrast that with a switch P4 interface that we see in this diagram, a typical switch interface has a parser and a parser blocks to begin and end the pipeline with a series of match action units in between to do a table match, and then you apply appropriate actions. And where while you are doing this processing, the packets sit in a packet buffer as a temporary storage. So now when we need to interface with the host, the data either originates in the host or ultimately terminates in the host after all the processing from the network. So you do need like a DMA like interface where you are able to read or write data in and out of the host, and to be able to process the data along the way, right? And once you say process the data, here we're not talking about just packet header processing, but you may have to manipulate the entire packets, the whole payload in terms of doing encryption, decryption kind of services, and doing checksumming or digest and the sort. And also you need to be able to trigger the events or indicate that the completion of the work in terms of like a request response. So the extension model that we have employed is, the execution model is you introduce a DMA engine at one end of the processing from the network. Let's start with the host in the network direction, where the host data or the work is indicated as part of an event scheduler, where you trigger or notify the SmartNIC from the host, typically from a driver interface, where you say there is a work or have some data to be transmitted or received, and you notify the event as a scheduler event. And that scheduler event, you can have an architecture where it's like a queue-based scheduler, where you can identify or classify the work or the messages that come from the host into different queues, and you at the granularity defined by the application. Typically, if it's an application like an RDMA, the queue could be at a granularity of an RDMA queue pair, or if it's a TCP processing that you're doing, it could be a granularity of a TCP connection, or it could be at a host device, like a granularity or a net device like granularity that you want to associate a queue with. And I mean, that completely depends on, specific to the application, on exactly what kind of services you are providing from the application. So once that, the scheduler basically will just schedule that particular work item as part of an event, which is associated with a memory address, which basically maintains a state or a context pertaining to that queue, which could be, again, like an RDMA connection block or a queue state, or if it could be a TCP connection block that's typically like maintained in like a per connection state in a typical Linux TCP stack, for example, is equivalent of that kind of a context that you need to maintain in memory, and that state that we work or operate on could be present in this NIC memory, and that particular scheduler event associates itself on a queue basis to the particular state in memory, and that where you could have both a table address where to launch a table from, and also a corresponding action pointer, which could be like a TCP transmit processing or a receive processing kind of an event. Or even going at a higher level, it could be an NVMe layer event of NVMe fabric connection or a namespace-based context processing. So the scheduler block introduces this notion of an event scheduling based on a particular type of work, and that in turn it just schedules a bunch of match action units to do a corresponding match on the table data in memory, and corresponding actions are executed, which again could be manipulating those data structures in memory where it's a stateful kind of work that's required. And then eventually at the end of all the processing, you packetize the data in memory into the packet content into the packet buffer. And that DMA operation can operate on either the data staying in the host memory itself or from the NIC memory. And then the switch P4 interface takes over to do any packet-based processing to be eventually sent out onto the network ports. So when it comes to the receive side from the network, basically once the switch P4 interface has processed and identified the kind of an application that needs to be triggered based on whether a flow is like a TCP flow, for example, or an RDMA flow, or it's some storage or some SDN kind of or a networking kind of a services construct. You can demux that particular packet into and generate a packet receive event to the P4 pipeline on a specific queue. And again, similar to the notion of a scheduler associated with a queue, you can have a queue associated on a particular packet too, and that queue identifier could be triggered by this by the switch in P4 interface, where that can schedule basically based on a packet event the corresponding application processing. Where you start operating on the received packet along with the corresponding metadata, which gives you the context of any parsed information. So the reason we don't have a parser kind of a block here to front end the host interface is because the packet has already been parsed, and that metadata can be carried over to this host RX P4 interface. So once the receive side processing happens, you eventually decide where or what particular host queue it is associated with corresponding to the host device, the PF or the VF device, and eventually you DMA the payload into the memory after the requisite processing. And depending on the type of processing that we do here, where if you're doing some like encryption, decryption, or any compression, decompression kind of storage services, things like that, there could be a temporary storage of memory of the data in the NIC memory to have, in the intermediate formats before the data eventually gets DMA'd into the host. So that's basically the execution model at a high level. Again, we're not going into a lot of details here, given the time constraints. We'll probably delve into a bit more details on exactly what are the considerations for each of these, memory or message-based manipulation of data in the next few slides. In addition to this execution model, the language itself where you have to define these services need some extensions. we have actually, done some extensions in terms of adding some loops and switch case statements kind of thing. It's more from a use from a development point of view. We'll talk about that a bit later. We also understand that the switch case statement has now been or being absorbed into the baseline P416 language itself. We have extensively done the backend improvements on our P4 compiler, where we have used the capabilities of externs, annotations, and table properties that are already there in P4 language by defining our architecture-specific constructs for the DMA engines, the schedulers, the timer-based events, and semaphores for the data integrity and mutual exclusion and the sort. So basically, the premise of this whole approach has been to enable or extend the line rate services that we do for networking traffic to the host applications, where you're able to do line rate at multiple 100 gigs, depending on the PCIe bandwidth. So what are some of the design considerations or the basic considerations that are needed to enable these services at the host interface? So the first thing, as we talked about, is that the triggers are based on events. The message interrupt events rather than packet-based events. The driver interactions with the host are in the TX direction. It's basically like a message passing interface where the messages can be stored in the host memory itself, but then a trigger is given to the scheduler to be for the smart NIC to wake up and start processing that particular message. And you also need interrupt capabilities to interrupt the host driver to indicate a completion of an event or a response. And there are, when it's a DPDK kind of a use case on the host, there's a pole-based mechanism where you may not need the interrupt based triggers, but it's basically the DMA of the completion of the data itself acts as a completion event there. But what the other consideration is, you need classification of the work. Basically, you need to understand what type of work is being requested from the host driver, and that basically goes hand in hand with associating the host devices or the host-based queues from the driver, whether it's an Ethernet or an NVMe, RDMA kind of drivers or crypto drivers, to the corresponding scheduler queue on the SmartNIC side to identify the class of work, and then you apply the corresponding service or you activate the corresponding application. This on-demand trigger can come from the host driver where you do the scheduler event, or it could also be an internally scheduled event based on where you have to chain a bunch of different P4 programs to process different functional blocks or functional handling of a packet or of a message before you can eventually packetize and send it out on the network. Like you might have to do NVMe layer processing and then a TCP layer processing. So those can be different sets of P4 programs that need to operate on this message to begin with, and then have to chain those services together. So you do need the scheduling capability to have like a multiple producer consumer like model where there could different producers can schedule the work for a particular consumer into like a work ring, and then be able to have the consumer do it in a specific sequence. So you also need timer-based where a delayed processing in certain cases where, typically protocols like TCP or RDMA transport would need retransmission logic and be able to clean up different queues based on timers and things like that. There are various timers that a typical TCP protocol state machine has, like delayed act timer, retransmission timer, and sort. So you do need to be able to schedule work based on a timer. So you do need some kind of a hardware assist or a construct to be able to, implement a timer. So when it comes to the data processing, so the messages themselves are, might be associated with a specific context, and you do need to maintain context across multiple packets or in the receive direction or the messages in the transmit direction, and that could need to be done at various granularities. You have, the granularity could be the messages pertaining to a specific host device or a specific host interface or a queue, or at multiple or like a subgranularity of queues within a device. So it could also be based on flows and connection states, where you have to keep track of, if you're doing a connection tracking like feature where you classify the traffic into different connections and maintain states or update TCP connection states across multiple packets for a given connection. So you also need to associate data structures across or state context across multiple layers. Like typically, it's like wherever a layer processing is involved. In the storage NVMe use case, for example, an NVMe volume might need to associate with a specific one or more namespaces, which effectively map to a particular queue pair with the backend target. And then that associates with a TCP connection that goes out to a TCP, a corresponding target at the transport layer. And there are cases where, a typical connection tracking is done as a man in the middle kind of an application where you're just maintaining some state for a given connection, and you update the connections, the sequence numbers and the ACK numbers and the state across packets. But you also may, in the case of an NVMe or TCP, for example, you terminate and originate TCP connections in the smart NIC itself, where there is no presence of the transport layer in the host. As we said, the NVMe block storage virtualization use case might involve just like an NVMe like interface to the host, and the NVMe over fabric abstraction is done at the smart NIC layer. So below that is where the transport TCP layer initiates. So the entire TCP state machine or a protocol state machine needs to be implemented at a TCP endpoint. And that would involve maintaining a lot more state in terms of the flow control and the congestion control states for the TCP connections. So what that means is basically the data processing is going to be more complex. You need to be able to read and write data from memory, where the memory, the user data could be in the host, but the data structure or the state context that you maintain is in the NIC memory. And you do need to be able to manipulate these data structures in memory, at line rate, for example. At each packet context, where you cannot really do how you handle typically a counter update, or like an account. You cannot have a separate region to do an extern based update of memory, but rather you do want to be able to do a load store like mechanism, where you read the data and then you modify it inline, and then you write it back for the next packet to look at the updated state. So that's where we kind of introduced something called a raw table, which we'll talk about next, where basically the tables in the match action units are able to read and write back to the same table. So in addition to when you're moving bulk data in and out of memory, whether it's from the host or the NIC, and transferring or converting the data from memory into a packet or packet back into memory, or in some cases, memory to memory, where you have to do intermediate processing, where you have an encrypted data before you submit to a crypto engine, or after when you're doing a decryption path, for example, or the vice versa. So you do need memory to memory DMA capability also. And in addition, each event that you process, whether it's a message event or a packet event, could result in one or more events. So it's not like just one serial processing of manipulating a packet and sending it out, but rather like as an example, when you receive a TCP packet, for example, you do the requisite processing at the TCP RX layer, and then you deliver the packet to the higher level application, which could be NVMe, for example. And in addition, you also need to, at the TCP transport layer, you need to also respond back with an acknowledgement back to the sender. So you need to schedule an event to do also a TX of an acknowledgement. So you do have multiple events or and you might have to packetize and send out packets when you receive a particular event. So you do have these multiple event scheduling that you need to operate on. So you have to have a capability for a P4 program to be able to schedule multiple actions. I mean, a DMA event and in addition, a scheduler event or a packetizing event, for example. Yeah, that's basically the data processing. So we'll talk a little more on the externs that we have implemented, that some of them delve into addressing some of these requirements. So last but not the least, in terms of the considerations, is the code maintainability. So far we are talking about a simple programming of defining a packet format. I mean, you define a parser, and then you define what are the actions to be done on packet headers in a switch kind of a P4 interface. But here you, I mean, depending on the applications that you're developing and you are implementing in this kind of a pipeline for performance needs, you might have to offload like really high-level applications, which like NVMe, TLS offloads, or L4 to L7 services, in addition to the transport layer, where these functions are typically done in like a higher level programming, like C or C++ kind of languages, where you assume like a general purpose load store kind of mechanism, and the complexity of programming and maintaining complex data structures and stuff. So you do need some kind of like a programming or a language capability, language and compiler capability, to be able to define these higher level applications and express them in P4. So that's basically, I mean, we started this approach with saying, okay, whatever extensions that we might need. So we'll be, we'll be looking into extending the language to do this. And we'll talk briefly about what are the extensions we've actually done. So coming to the language/compiler extensions, again, a lot of these are not language extensions that we talk about here. It's mainly the P4C front end was, we didn't have to extend a lot, to be able to achieve the programming at like the NVMe or TCP layer applications. But we'll start with describing the externs that we have leveraged. I mean, these are architecture-specific externs that we have implemented. So starting with like a raw table, like we talked about, where the match action units will need to, basically it'll load into memory a raw memory address, rather than having to scan and match through a particular entry given a key in a hash table or ternary table kind of thing. Here you need to just say the application defines that this is the table, like a TCP context table, for example, for a connection that you want to load. And you just say this is the raw memory address that you want me to load into the the MPU. or the processor where you want to act on. And you just set up that table match to a raw memory address. So that's one of the extensions that we've done using table properties, and this is done as an extend function. And also, so the action have to be also, I mean, it's not coming from the table itself or the table entry definition itself in this case, but rather depending on the flow of the code or the logic, you might have to load different actions. And these are set up from like typically previous actions. So like one action routine can say, okay, you load this table as the next action, and then go through and also load the corresponding action based on a specific table. So this action reference is actually defined from the previous action code itself instead of a table entry. So, and scheduler events again. So these are basically instructions to set up the hardware to say, okay, what is the specific queue that you want to schedule an event on a specific, for corresponding to a specific application. And timer again could be, you set up a time at which you want to schedule a particular event on a specific queue. So those are defined as externs. And the DMA commands are also defined as externs, where you define a series of one or more DMAs, and it could be like a scatter gather kind of things where you might have to manipulate or build different packet headers in different locations in memory, but you want to call is all of them and packetize in a contiguous block to build a full packet. So basically you need one or more DMA commands to be able to pick up different chunks in a specific order, and you define the sequence of these DMA commands on how exactly you will DMA into the specific location into the packet buffer. So the memory. So in addition, you also have use cases where you might want to just go and update some specific memory from the action routines, where it's just like a raw memory read or a memory write operation. So even those come in handy in certain cases, whether you're updating atomic counters kind of thing, or in some cases you might have to trigger another program based on a memory event, or updating a memory in a location where the other program might be polling on or watching kind of thing. So those are also added as externs. Counters and rate limiters, I mean, these are already there in the base definition of the language, or it's a standard extern, it looks like. So yeah, and any triggers that we do to engage the encryption, crypto blocks, or hash engines and things like that are also done as externs. And this is not an exhaustive list. These are some of the key extents that we have added, which are specific to the architecture. And so going to the annotations, so there are some specific annotations that we have introduced also, specifically, just giving an example here, the add _ ref, basically it indicates that the data that is loaded from the table is actually a writable data. It could potentially be written back to the table itself, and where in a typical or a base P4 definition, the data that's read from the table is read only, but here we're making it a read write kind of a data where you might have modifying the data, and it gets written back. And there are semantics or the hardware capabilities that are available to ensure that this data is written in an atomic fashion. And if you have other packets, working on the same kind of data, they get serialized, and you ensure atomicity in updating this data. Yeah, so we do have, more annotations that are done to, which are specific to the architecture, where you say you align particular fields in the structure at specific byte boundaries. This specifically to ensure that the performance in processing these messages are, is guaranteed to be faster. And you can also pass parameters into these action routines from the control plane, where you can symbolically reference a particular a value that is not known at the programming time, but you might have to the control plane typically, for example, can set it up to say what is the value of a particular symbol could be, or it could be a memory address, or a value which is not a constant that is known at the programming time, but you could access it dynamically in a program. So from a new constructs perspective, I think we've just introduced loops where it's just more on the ease of programming rather than like a must-have kind of a scenario. Where wherever you have need for iterating through multiple entries, whether it's processing multiple descriptors or building multiple DMA commands or going through multiple entries in a TCP queue, for example, you do need to be able to do a loop construct. So that's basically one of the only new constructs that we have introduced. And so far, we've been able to get away with just using the extends and annotations otherwise. But I think this is still a work in progress, and we are building more and more applications for these use cases, and we might be considering more extensions as needed. So jumping into a typical host network workflow, just to give an example of or an explanation or illustration of how a flow from the starting with the driver in the host all the way to the packet going out on the network would happen. So you do have the driver like triggering an event, like we talked about through the scheduler, where it has this taking an example of an NVMe write command, for example, an IO request that the driver is trying to do. So it basically would write the data into a send queue in memory, and then it would post a request or schedule a request to the NVMe queue in the NIC to say pick it up and process this message, which would trigger basically a P4 program which would do the NVMe request handler. Basically, the light blue blocks over here, each of these can be are P4 programs which can be basically run on multiple match action units to basically do the functional processing of an NVMe request handling, where you might have to parse the command from given in the request and map a corresponding NVMe IO to the corresponding NVMe backend session or a namespace, and then figure out what is the next action, which in this case, we are illustrating an example where an NVMe PDU would need to get encrypted with XTS encryption at rest, and then go to, do a digest on the PDU, as per the NVMe or Fabric's standard spec, and then hand it over to a TCP transport layer, which will do that stateful TCP processing of the packet before it, of the data before it packetizes and sends it out. So the blocks here is basically each of the programs which handles a specific functional aspect of the message can hand it over to the next level of the program using a scheduler event. And these programs can also use external events in the case of using an XTS engine or a hash engine to schedule the corresponding crypto operation on the data. And then in the end, so there'll be a packetizing event, and any memory operation is going to happen based on DMA requests. And these programs in the match action units themselves will have to manipulate the memory based on the context of the state that they maintain, using the table, the raw table and the write back mechanisms of maintaining stateful data. So the data structures themselves are manipulated by these programs, whereas the user data is basically managed using DMAs, where you DMA the packets from the host memory onto the and the XTS engine would read it and then write the encrypted data to the NIC memory as a temporary storage. And then the hash engine computes the digest on it based on the request descriptors that are set up in this pre-digest P4 programs. I mean, these programs are basically used to set up the requests into these hardware engines and call like a hardware API invocation to do the corresponding encryption or the hash operation. And ultimately, the TCP TX program would pick up the final data that is computed as an NVMe PDU, and then it would packetize it by adding a TCP header and then DMAing it into the packet buffer, where the L3 processing and below happen in the switch P4 blocks before the packets are sent out on the side. So there's a corresponding network to host sequence that you would do where the trigger starts with a packet receive event into the TCP control block, and you go through the sequence of writing that packet into memory and subject it to the hash digest verification, where you validate the header and data digest on the NVMe PDU, and then you do the decryption of the data. And then once the decryption is done, you post a completion into the driver, and this could be triggering a DMA into the interrupt block to be able to wake up the driver in the host. So that pretty much describes the sequence of how the scheduler block and the DMA blocks work in conjunction with these P4 programmable the match action units program engines. And the software basically drives the whole sequence of, how these these services are applied to the host interface. So, in conclusion, so we see that the P4 switch interface can be extended, and the P4 interface is conducive to extending the programmability to the host interface. With some hardware-specific extensions, we are able to achieve, these services and be able to co-locate, services, the networking, the storage, and security services, and able to, realize performance at much higher, line rates compared to, how we would do it with a fixed function logic and or a general purpose CPU combination.
So thanks so much. That's really, really cool to hear. I have many questions, probably more questions than we have time for. So I'll just run through until our slot is done. Mm-hmm. So maybe to start with a really high level question, why P4? What are other solutions that you could have used? You talked a little bit about maybe writing C code in parts, but can you talk a little bit about Pensando's thinking around using P4 in this kind of device and what some of the trade-offs are, benefits and challenges? Sure.
So for us, extending P4 was like a logical, kind of an approach, specifically because our product did have a P4 switch interface where we are trying to, support it as like a distributed services card, where you try to bring in the functionalities that are typically done on switches and routers or the network appliances. From L2 all the way to L7 kind of services into our Pensando product. But at the same time, when we started looking into extending into the host interface, other than how you schedule these work items and how you interface or interact with the host, and how was pretty much the only extension from the hardware perspective that we needed to do. But from a P4 perspective, we could leverage the whole pipeline paradigm, the multi-processing paradigm that you would do, and the table match action that we typically do in a switch interface is just the way we could extend to just reading the data from memory instead of just a fixed table that we do for packet headers. So it was like just like a logical extension that we had to do rather than inventing a new paradigm and and an architecture to be able to, I mean, whether we do it from C, if we had to then involve implementing a C compiler, writing to our hardware specific machine code. But the extension of the P4 compiler, the P4C that's already there was pretty much like an incremental effort for us.
Cool. So another question, you described a bunch of really cool scenarios, including storage and VME and crypto and of course all the traditional offloads. So are there network functions that you think are kind of fundamentally out of scope? Like what's the limit of how far you could push this? Or the things that would be really challenging based on the current abstractions and capabilities that you have?
So, so we actually have approached, applying the networking functions in a modular fashion, where you just, provide the Ethernet I/O interface to the host, where you handle the various, the standards that are there to interface with, like the VirtIO, VDPA, like standards, or specific use cases with VMXNet or the UPT, the pass-through, universal pass-through functionality, where you just interact with Ethernet layer. But once you classify the traffic as Ethernet, and then you can introduce stateful services to apply at any networking layer, for example. So we are kind of able to do QoS, for example, based on classifying these host traffic at different layers, do rate limiting, do shaping of traffic, things like that. In addition to once you interpret a particular Ethernet payload as a specific type of traffic and classify as at the layer 3, then you can apply any further service on it. Whether it's networking L3 services or L4 to L7 stateful services. So so far we are able to pretty much do a lot of these appliance like functionalities too, and apply them to host traffic. The challenge or going forward, as some of these are still work in progress, is to ensure the performance of it mainly, right? So when it comes to, some of the services that you can think of is not very conducive to P4, for example, is doing like a full HTTP layer or L7, like parsing kind of capabilities, which unless you have like a real hardware acceleration, you may not, it's not very conducive to defining, complete regular expression processing, for example, in P4, right? So those are some of the things which we are not ventured into at this point. So we do have, kind of ARM processors also co-located in the NIC, which we can, work in conjunction with and able to onload kind of a thing from P4. So some of these services that make more sense to handle it in the ARM or general purpose CPU like processors.
So I know we're basically out of time, but if I can just ask for a really quick answer, any plans for pushing some of these extensions into open source?
Sure. So I think we will start looking into this. I think we'll definitely start participating more in the P4 community, and we can probably start with looking into some of the externs that we have done internally, and maybe make them into standard externs in P4 to begin with. And maybe, yes, the loops, for example, is definitely something that we should be able to absorb.
That would be wonderful. I know Pensando has been very active, especially in the architecture group, and it's great to see these ideas that come up from specific targets and use cases get out there for the whole community. Okay, so I think we're out of time, but thank you so much. That was a great talk, and looking forward to seeing what comes next for this work at Pensando.
Thank you very much.
Thanks.